This lecture extends the discussion from the previous lecture video on the different type of forces we are dealing with in this course. Here I introduce you another force called spring force. Some literature refers to it as elastic force, as what we are going to learn soon is applicable to all phenomena pertaining to stretching and compressing of elastic material. We are going to use spring as example in this lecture, but it could be rubber band, elastic rope, etc. This is the problem now. If the spring has a constant 20.0 Newton per meter, how far will the spring get stretched in order to hold still a 10 kg crate as shown in the figure? You may assume that there is no friction between the crate and the ram. Now don't be bothered with this weird looking contraption. I came up with this example to explain two things at the same time. 1. The concept of spring force, and 2. How to solve dynamics problem on slanted surface. It is a relatively simple problem, but there are a lot we can learn from this. Now let's get ourselves up to speed. I will not draw the forces on the free body diagram one by one like what we did in the previous videos. Instead, I will draw them all at one go. Since we are drawing force body diagram on the crate, let's remove everything else from our mental picture except for the crate on the ram. Go through the list of the forces we discussed earlier. Are they applicable in this case? Starting with the applied force, is there any external agent exerting force on the crate? There indeed is, except that this time around, it is no longer a man pulling the crate, but a spring which is firmly attached to a pole. We will study this force in detail soon. How about weight? Obviously, any object on Earth is influenced by gravitational force. It is pointing down toward the center of Earth, and straight away we can compute the magnitude, W equal to mg. How about normal force? The crate is not sinking into the ram. Hence, there must be a normal force acting on the crate. As we learned earlier, this normal force has to be perpendicular to the contact surface. Hence, the normal force is perpendicular to the surface of the ram. Is there a friction force in this case? No. The problem already explicitly said no friction. So that's it. Three forces only are acting on the crate: the applied force from the spring, the weight, and the normal force. The problem, however, also mentioned that the crate was to be held still by these forces. Held still, that's the keyword. It is not moving, it is at equilibrium, which means the net or resultant force has to be zero in accordance to Newton's first law. That further implies that the three forces have to cancel one another. So the next question is, how do we ensure that the forces cancel one another? The first thing you should immediately realize is that the forces are not aligned along any two perpendicular axes, and hence we can't just simply add them along x and along y and set the respective net forces along horizontal and vertical to be zero. We have to resolve those forces which are not yet along x neither y before adding the component. In the first place, what is considered horizontal or vertical when the ground itself is slanted? Well, if you recall what I mentioned in Lecture 3, the choice of coordinate system will not change the physics behind, and therefore we shall choose a coordinate which gives us maximum convenience, and we shouldn't worry it will affect our answer, provided we are consistent and do not make any computational mistake, of course. Given the setup, there are two natural ways of defining a coordinate system: this way or this way. I will suggest that we adopt the latter. Why? Because if we are using the first coordinate, only weights are already aligned along the vertical axis, and hence we will have to resolve f and n. But if we are using the latter, f and n are already aligned along the horizontal and vertical component of the coordinate, and we just need to resolve w. Less number of forces to be resolved means lesser amount of work and potential mistakes. That's what I mean by choose a more convenient coordinate. Will you decide to choose the former? Please go ahead. We will adopt the latter coordinate in this video. So when I said horizontal, I'm actually referring to the component of the forces along the surface of the ram. And when I said vertical, I'm referring to the axis which is perpendicular to the surface of the ram. Alright, so how do we go about resolving the weight? Well, first you need to realize that this angle is the same as the inclination angle of the ram. Magic? No, it's just geometry. First, you have to realize that this triangle is similar to the triangle that forms the ram. Remember our definition of similar triangle when deriving centripetal force in Lecture 4.5? If they are similar, this angle will have to be equal to theta. By the way, Sorry that the corner of the triangle gets cut off, so just add that corner back in your mental picture. Now, if this angle is theta, then that angle has to be 90 degrees minus theta. The resolutions of the waves have to be perpendicular or 90 degrees to each other, which means this angle must be 90 degrees minus 90 degrees minus theta, which is equal to theta. Finally, the so-called vertical component of W will be given by W cosine theta, or mg cosine theta, whereas the horizontal component will be given by mg sin theta, and we can do away with the resultant waves so as not to confuse us in the subsequent calculation. In short, we just resolve mg into mg cosine theta along the y-axis and mg sin theta along the x-axis of our chosen coordinate system. This is also a convenient way to write the resolution of mg in terms of the inclination angle of the ramp. So far so good. With this free body diagram in mind, we can solve for the normal force and the spring force. Similar to the argument in the previous video, since the crate is not moving as far as vertical component is concerned, the net force along the vertical has to be 0. This implies normal force and mg cosine theta cancel each other. Hence, although it is not required in this problem, we can obtain the normal force is approximately given by 85.0 Newton. Similarly, the fact that the box is held still implies that the net force along the horizontal must also cancel each other. The rest is algebra. The applied spring force is equal to 49.1 Newton. But this is not the end of the story, for what the question asks is not the magnitude of the force, but how much the spring has to be stretched to produce this amount of applied force to the crate. To get to the answer, we will need to study in depth the nature of spring force. Grab a spring if you have one around you. The easiest one is probably by dismantling those retractable pen you may have in your pencil box. Play with it, stretch it, compress it, and observe. The first thing you should realize is that the spring has what we call an equilibrium state. That is when it is at its original length, neither stretched nor compressed. To stretch or compress the spring, you have to apply force. The amount of force you need to apply depends on two things. 1. The construction of the spring, and 2. How much the string is stretched or compressed. Stretching a thick spring made of steel, such as the one used for car suspension, is definitely different from stretching a thin plastic spring used in those slinky toys. The difference in the spring's properties is captured in the spring constants. It is denoted by small case k and has an SI unit of Newton per meter. A larger value of spring constant means a larger amount of force is required to stretch or compress the spring, as one requires from stretching or compressing spring of lesser value of constant by the same amount. Let me repeat that slowly. A larger value of spring constants means a larger amount of force is required to stretch or compress the spring as one requires from stretching or compressing spring of lesser value of constant by the same amount. In short, a spring with a large constant is a stiff spring. Then, more force is required to stretch a spring over a longer distance as taken from its equilibrium. As a matter of fact, it is tougher to stretch an already stretched spring than to stretch a spring from its equilibrium. All these factors are captured in this simple formula F equal to negative kx. But wait a minute, why is there a negative sign there? When you stretch and compress the spring and release it, notice the direction where the spring recoils back. It always recoils back toward its equilibrium. If you stretch the spring to the right, it will recoil back to the left. If you compress the spring to the left, it will rebound back to the right. In short, the recoiling elastic force that the spring has is always opposite to the direction where it is being stretched or compressed. That's the meaning of the negative signs in the equation. If you simply ignore the negative sign, by the way, this is something that may probably bother you, that we can just remove a negative sign from a mathematical equation. In fact, I can tell you that some literature actually presents spring force as F equal to negative kx, while some others as F equal to kx without the negative sign. Once again, I would like to reiterate that the negative sign in this equation implies the opposing direction of the force and the extension of the spring. If magnitude is what you are concerned, you can always ignore the negative sign. Okay, coming back to what I'm about to say, if you simply ignore the negative sign and concern only with the magnitude of the force as a function of the spring extension, The spring constant K serves the role of gradient in the plot. It is easier to appreciate now that a spring with large constant or a stiff spring has a steeper gradient. It takes a tremendous amount of force just to stretch such a spring by a little. Furthermore, there is a limit to how far you can stretch the spring, as you might have probably experienced. When you stretch a spring or rubber band excessively, there will come a point where it is no longer be able to recoil back to its original or equilibrium length. It has been deformed, and the effect is permanent, like when you stretch plastic bag apart. Technically, we say that the spring or the band loses its elasticity and it becomes plastic. While it is stretched within its elastic limit, the plot will be linear as predicted by the equation. Beyond this limit, it is no longer a simple equation f equal to kx to describe the phenomenon. The plot is no longer linear either, and it definitely does not extend forever. If you pull the spring really hard, it will break eventually. So let's get back to our problem. Now that we know the equation that relates spring force to the extension of the spring, we can equate this equation to the force applied on the crate we computed earlier. The spring will have to extend itself by 2.46 meters to hold still the crate. This concludes our problem.